No. All right, so let's see, can we recap? No, it's too much to recap, whatever. All right, we're picking this up from 20 minutes, half an hour in. Yes?
You have to multiply those backwards in order to get the identity.
Yeah, so the whole point in doing this is to deal with the identity matrix. Not only do we have to multiply it backwards, but we have to multiply the inverse. So it turns out that if you're interested in the inverse of A, we would take the inverse of both sides. And we know that the inverse of the identity matrix is the identity, right? And we know that the right-hand side is just the identity matrix again. Do you remember the inverse of a product of matrices? How they look like? The inverse distributes and the order switches. Remember that? And we said that we did it for a product of two matrices. And then we said, by induction, this will work for everything. But we didn't prove it. Did we? Or did we?
We proved it for one way. We said it's similar.
Oh, okay. All right. So now if we're going to want the inverse of this product, we're going to want to take the inverse of each one. And then since matrix multiplication is not commutative, it actually followed for this case that the inverse is going to be the product in reverse order. Yeah, that just brings it over on the other side. So that is what we're looking for eventually, is the inverse of A. So we want to find out the inverse of A. Oh yeah, I guess so. That was even better. I wanted to use the inverse of products rule. Hal said this thing altogether is the inverse of A, since that is equal to identity, and that is correct, absolutely correct. But I wanted to take the inverse of both sides and then do this distribution. And now, if I were to multiply this over to the other side, I want to bring the E3 over to the other side, so I'd multiply both on the right side by E3. So this is where it gets more cumbersome than Hal's method. I would say A inverse, E1 inverse, E2 inverse, E3 inverse, and I'll leave some space there is equal to I2. And I would multiply this by E3 on the right side, and that would get rid of this. And then I'd move on and continue the same process. And then I would get basically this little box over here. And so identity times anything is identity, and you just have A inverse is equal to E3, E2, E1 in that particular order. So to find our answer for the inverse of the inverse of our original problem, we can just simply take E3 times E2 times E1, which is 1, 0, 0, negative a half, 1, 0, 0, oops, this is 1, 1, 0, 1, and 1, 0, minus 3, 1. And if we multiply this, we should get the inverse of A. So let's see. It's associative, so we could take any two that we want. So I'll take the first two. I'm going to get first row, first column is 1. First row, second column is 1. Second row, first column is 0. Second row, first column is negative 1/2. And then multiply this. First row, first column is negative 2. First row, second column is 1. Second row, first column is positive 3/2 and negative 1/2. Yeah?
So back when we were finding the inverse, could we have just like taken the A outside of the bracket with the inverse and applied the inverse to it and then kept the E3, E2, E1 in brackets with the inverse and just multiplied each side?
Right here?
No, down here.
This one?
To the right. Right there.
Yeah.
Could we have just pulled the A out and then multiplied each side by the entire E3, E2, E1 inverse? And found it that way too?
Yeah. Yeah, there's several ways to do that. I think this is the most clever if you just identify this product as one whole matrix multiplied together, and that's the inverse. The other way to do this is if you can multiply, or you can multiply by A inverse on both sides, and then that would get rid of that A, and then that'd still be equal to that. So I clearly took the long way, but it's still okay. All right, so this is our actual inverse, and we could, since we know the inverses of A, of 2 by 2 matrices, by heart already, right? It's 1 over the determinant times switch the diagonals and negative the wings. So the determinant is 4 minus 6 is negative 2. Negative the switch diagonals and negative the wings. And if we work all this stuff out, we're going to get the same result as what we had. Just to double check. Yeah.
How do we get rid of way on the bottom right? How do we get rid of the I?
Oh, the I is the identity, so anything times the identity is itself.
Okay.
And so that just, it's like multiplying by 1. Okay, are we good with the elementary matrices and how they're related with the elementary row operations? So if we can define these elementary matrices, and then whenever you want to do something with a matrix, say switch the rows, and then you just multiply it by the appropriate elementary matrix, then you can do that mathematically without having to, again, tweak the insides of the matrix. You just do a regular matrix multiplication. Okay. So I think you guys will have some homework on trying to find elementary matrices. But here's a theorem, probably won't prove. Let A be an elementary matrix obtained by performing an elementary row operation on the identity. If the same elementary row operation is performed on an n by r matrix, the result is going to be the same as multiplying. We already showed that. Without actually proving it, we kind of showed this particular theorem. All right, let's take a look at the inverse of these matrices. Each elementary matrix is invertible, and its inverse is an elementary matrix of the same type. So for this, let's take a look at the example where we did a 3 by 3 matrix. And we did some stuff to a 3 by 3 matrix, right? So I think we named it E1, E2, E3, or something like that. No, we didn't name it yet. Sorry, let me go back. I wanted to copy these matrices that we did. There it goes. So, we went from the identity matrix and we did a couple of elementary row operations, and then we got these as our elementary matrices. And I'm interested in finding the inverse of these things. So what would you do to get the, let's name these matrices. Let's call this E1, E2, and E3. So I'm interested in finding out E1 inverse. So what do I need to do to make this look like the identity matrix again? So I would need to multiply this by 1/2, right? And so what I would do is I would take my identity matrix and multiply this by 1/2 R1, and then that's going to give me 1/2 0 0 0 1 0 0 0 1. Say it again? Oh, I'm not going from here. I'm going from the identity. So it's that thing that I want to create an elementary matrix. So if I were to multiply E1 times E1 inverse, I should get the identity matrix, right? So I check this by saying E1 times E1 inverse. E1 is 2 0 0 0 1 0 0 0 1. E1 inverse is 1/2 0 0 0 1 0 0 0 1. And if I were to multiply this out, I'm just going to get the identity. Okay? So this type of elementary matrix, where if I multiply a row by a number, has an inverse, and its inverse is multiplying the same row by the reciprocal of that number. Does that make sense? All right, if we swap rows, what do you think the inverse of that's going to be? swapping it again, right? If we swap row 1 and row 2 and we get this elementary matrix, if we want to get back the original identity matrix, we would swap the same rows. So if we start from the identity matrix I3 and do a same row swap, this is going to be the inverse of our second elementary matrix. So we can check that as well. E2 multiplied with E2 inverse. By the way, we should be checking both the switched order, A and A inverse and A inverse times A in that order, but we'll just say it's correct. 1, 0, 0, 0, 0, 1, 0, 1, 0. And if you multiply this with the same thing, you're going to get the identity matrix again. Okay? All right, the last one. How would we find the identity matrix of something where we do how would we get the inverse of this? How would we go back to the identity? What would I want to do? So I'll take row 1, I'll multiply that by positive 4, and then I'll add it to row 2. And then replace row 2. So from the identity matrix, if I were to go from the identity matrix, I'll take row 1, multiply it by positive 4, add it to row 2, and so row 3 doesn't change. So the identity or the inverse matrix of a row operation or elementary row operation where we multiply a row and then add it to a different row is almost the same thing, except instead of a plus it's a minus, or instead of a minus it's a plus. Okay? And then you can do your check here. You can check to make sure that this actually gives you the inverse or the identity. So these, by the way, are 3 elementary row operations. And you can mix it up. You can, switch different rows, or you can multiply different rows and add it to a different row and things like that. But essentially, it's multiplying a row by something, switching 2 rows, or multiplying a row by something and adding it to another row. Those are the 3 elementary row operations that we've learned in solving for systems of equations and in finding out inverses. And so these are the inverses for those elementary matrices. Okay, it's the same type of inverse, except it's slightly different in that you could be multiplying by the reciprocal or multiplying by a negative and adding it to a different row. Questions? Wow. All right. Yeah.
If I were a linear algebraist, I would use one of those 2.
Probably. Or you'd let the computer do it for you. Okay. Let's see. Is it changing colors? My screen just kind of changed here. All right, let's see what else we got here. So we got a theorem. This theorem is kind of a taste for a bigger theorem that we're going to be dealing with later on. And I don't think we'll be proving much of this today. But whenever you see the fundamental theorem of something, it's like a big unifying theorem that ties in a bunch of different ideas in that particular course. Like the fundamental theorem of calculus ties in the idea of derivatives and integrals and puts it together. So here we have the fundamental theorem of invertible matrices. And the first version goes 1 through E. The second version is going to go through F or J or something like that. And then it's going to keep going and polish off almost all of the alphabet. But this is the first version of it. Okay. Matrix is invertible. And by the way, they're saying all its equivalent so that if you show that a matrix is invertible, then you've essentially shown the rest of this as being true. Or if you show that you can reduce a row echelon form, the reduced row echelon form is the identity matrix, then the rest is true. Okay, so these are all equivalent. It says that matrix A is invertible. Then A times X is equal to B has a unique solution, so this translates to a system. We have a system of linear equations with a coefficient matrix being represented by A. And if that's equal to B, then this has a solution.
So the unique solution is the vector x, right?
Equals, well, the vector x is the variable, so the unique solution is technically A inverse B. So maybe we can say that. So A is invertible says that A inverse exists. So this has a unique solution, and your unique solution is actually A inverse B. Because it's invertible, we can do this matrix algebra. Ax equals 0 says that we only have the trivial solution, which means the only way this would be equal to 0 is that if x is equal to 0. And by x is equal to 0, I mean the 0 vector. So x, if it's x, y, z, then it'll be 0, 0, 0. If it's x1, x2, x3, x4, then it would be 0, 0, 0, 0, depending on however many, what your dimension of x is. The reduced row echelon form for A is the identity matrix. And A is a product of elementary matrices. A is a product of elementary matrices. Well, the inverse is in reverse order. So I think the other part that I want to get out of this from the example that we had earlier is that, remember, we had it as E3 times E2 times E1 times A is equal to the identity matrix. And I was interested, back then I was interested in finding out A inverse, but if I wanted to solve for A here, I would multiply this thing by the inverse, right? So I'd multiply this by E3 inverse. And then they would cancel, and then I would multiply this by A2 inverse, or E2 inverse. And then they would cancel, and I will multiply this by E1 inverse. So after doing all the canceling, A will eventually equal to E1 inverse, E2 inverse times E3 inverse. Now remember that the inverse of an elementary matrix is also an elementary matrix. So these are all elementary matrices. And A then is a product of elementary matrices. So regardless of how far we go with E1, E2, E3, we could have gone to E17 or whatever. But if we lay it all out, it's a product of the inverse of elementary matrices to get the inverse of A, which is still in its own right an elementary matrix. Okay? All right, so that's our theorem. And if we were ever asked to solve for a system of equations, we can tell if this has a unique solution if we can find the inverse of A. Or we can tell if we can row reduce row echelon form A into the identity matrix. Or you can tell if you just look at the matrix of coefficients and then seeing that they only have the trivial solution. By the way, this is, it's going to relate to linear independence of columns and stuff like that. So that's the part where version 2 or version 3, we're going to have more stuff to it. Well, kind of.
And then they're like, well, there's going to be part 2.
Yes, but in a different sense. So part 1 and part 2 of the fundamental theorem of calculus proves a two-way relationship between the derivatives and integrals. This is not half of the proof. This is just half of the equivalences, and then we're going to add more equivalences to this. So it's a little bit different. Okay. And some of this idea here, the last two theorems in this section, these ideas were kind of brought up already. From our last lecture, we talked about finding the inverse by appending or having appending our matrix A with the identity matrix, and then a bunch of elementary row operations to make that left side the identity matrix, and whatever you got on the right side is going to be your inverse. So that's what this is saying, and this is based on the elementary matrix theories that we've just been studying. And then this one talks about the uniqueness of the identity matrix, so we can just look at it from one side. Okay. That kind of closes that section. I was interested in seeing if there was a problem that we can do from homework from this section. This is 3.3. Oh, I didn't get my stuff ready. What do I want? I want. These things are going to have the answers. I have to look at the student.
I think you could check right at the top. No solution.
Oh, really? I didn't know that. Okay, I'm here already, so. We interested in really, if I was going to do one, I'd just do the first one or the second one. All right. All right, let's do problem number 2. We have two matrices A and B, and they want to know the elementary matrix E that satisfies the given equation. So they go from B, and they multiply it by some elementary matrix that just they start with B, and then they go to A. And so what I want you to do is look at B, and then look at A, and see what elementary row operation did they do to get A. What elementary row operation did they do to B to get A? All they did is switch the rows. So B to get A, All they did with which two rows? The first and the...
0, 0, 1.
Yeah, I think. Wait, whatever. So all you do is you take your identity matrix. This is a 3 by 3 identity matrix. And then do that operation, row operation on that, which is switching the first row and the third row, and then that should be okay. So switching the first row and the third row would look like this matrix, and if this is what we type in, we should be good.
Yes, no.
All right. Partitioning a large square matrix can sometimes make inverses easier to compute, particularly if the blocks have a nice form. Using block multiplication, compute the inverse of the given matrix partitioned as shown. Assume that all inverses exist as needed. And recall that O is a zero matrix. So let me write this a little bit bigger. A, B, O, D. And this matrix is broken up into this. The bird. Probably not. No, because this is coming from a bigger matrix. So what we want to do is we want to assume that the sizes will fit, because this might not be a square matrix. They're assuming, oh, this is a square matrix, but the partitions might not be square. So let's just assume that this is going to get partitioned so that it'll work out. And what we're going to need is we're going to need to know these 4 different parts of your new matrix, which is going to give you the inverse. And if it's supposed to be the inverse, then the product of this will eventually give you your identity matrix. So what we want to know is we want to know what I need variables. We want to know what star and asterisk and box, and I don't want to use a circle. Let's use a triangle. Pentagon. So if you do the regular matrix multiplication, these star and asterisks and square and triangle are not numbers. They're actually matrices, and they're matrices that are different sizes. Could potentially be different sizes. If they were all square matrices, then that would have been great, but I guess we have to kind of assume that they're all different. And so if we were to do a matrix multiplication on this, pretending they're like 2 by 2 matrices, we have A times star. My A looks like a star. Maybe I'll write my A a little bit carefully. Plus B times square and then A times asterisk plus B times triangle, and then zero matrix times star, which will disappear because that's a zero matrix, plus D times box, and then 0 times asterisk plus D times triangle. I scribbled them out because there's zero. There's zero matrix being multiplied. So, if this in fact is the inverse of the original matrix, then we should have zeros in different places, right? If this is supposed to be the identity matrix, then I can pretty much guarantee that this and this should equal to 0. Okay, because you should have 1s in the diagonals and 0s everywhere else. So if it's not along the diagonal, then that's going to have to be 0. So if D is a non-zero matrix, D times square has to equal to 0. What can you say about square? So D times square is 0. That must mean that square has to equal to 0 because D is whatever D was equal to. And so the square matrix has to be 0. Or the square part of the matrix has to be 0. So this is 0. Does a square exist anywhere else? The square is 0. So once we've established the square is 0, then this is also going to be 0. Yeah, but if you know that your output has to equal to 0, oh.
Yeah, so this is a matrix. So like you can't say that square is 0. Something that the inverse of D or not.
But something else?
Yeah.
I don't know.
When I did this with like the wing,
Uh-huh.
I got them all right except for the one with the 0.
Mm. Well, let's keep going here and see if we can get further. So it looks like that's going to be 0. We have then we have A star has to be, now this has to be the identity matrix on either side, so this has to be the identity matrix. So what does star have to equal to? The inverse, right? So if you multiply both sides by A inverse, then star has to equal to A inverse. And that would go the same for the bottom over here, right? D times triangle has to equal to the identity matrix. So D is equal to D inverse. Or I'm sorry, the triangle is equal to the inverse. So the only thing left to deal with is this top part, where A star plus B triangle has to equal to what? Has to equal to 0. Let's see. So we just need to find star because we know what the D is. The delta, the triangle. So A asterisk plus B, and this is D inverse. The triangle is D inverse is equal to 0. So if we solve for this, we would subtract. Let's see. I guess asterisk was not a good symbol. So if we want to solve for asterisks, we would just take the inverse of A on the left side, so that asterisk is equal to A inverse times negative B D inverse. And that negative number, negative in front of that is the scalar that you can just take out outside. So you could, if you want, I don't think it's necessary, but you could take that negative all the way out since it's associative and all that stuff. So that should be your matrix. Your matrix should be A inverse. And then this one's a little bit more complicated. A inverse, B, D inverse. And this would be 0. Oh, minus. And this would be 0, and this would just be D inverse. Yeah. And it was what? Well, let's see. A inverse, right?
Yeah, you have to enter as O, not as 0.
So,
Yeah, because that's what O represents as a 0. Every y'all should work. Just don't type in the 0 for 1, 2.
so capital O, right?
Yeah.
And then D. So I think that's what I had. Let's try. Better be right because we're out of time.
Yeah, it works.
So looks like it worked out okay. It's not quite scalars, but we're doing matrix algebra is what we're doing. All this stuff that we're doing is matrix algebra. Yeah, but you're looking for the inverse, and I think this is assuming that it's an all invertible. Yeah. No, because they're not scalars.
I know, but you can do that instead of right answer. You can simplify it.
But it wouldn't be, would it?
Yes, it did. It worked. That's the way I did it.
Okay.
Like.